now we have studied the propagation characteristics and salient features of optical fiber and optical waveguides. So, I think now it is time to stop for a while and have a recap of whatever we have done till now. So, in order to understand propagation characteristics of optical fibers, we have first understood how an electromagnetic wave propagates in an infinitely extended dielectric medium. So, infinitely extended dielectric medium, n square is independent of x, y and z. So, it is homogeneous medium. Then an EM wave propagating in z direction has an electric field and magnetic field given by E z t is equal to E 0 e to the power I omega t minus k z and H is equal to H 0 e to the power I omega t minus k z. So, this has x, y and z all the components, and we had shown that for such a case E 0 z and H 0 z are 0. So, this is a transverse wave. For a linearly polarized wave which is polarized in x direction and propagating in z direction, I can write the components as E is equal to x cap E 0 e to the power I omega t minus k z and H is equal to y cap H 0 e to the power I omega t minus k z, where H 0 and E 0 are related by this. So, I see two things. One you should notice that this E 0 and H 0 they are constants. Okay, they do not depend upon spatial coordinates, and also that this is purely real. So, H and E are in phase. I can also write it down in terms of B, since B is equal to mu times H. So, B would be y cap B 0 e to the power I omega t minus k z. So, the amplitude of B is 1 over V times E, and so the amplitude of B is really much smaller than the amplitude of E. Then we had considered propagation in waveguides. So, now if n square depends upon x and y and the wave is propagating in z direction, then the electric and magnetic fields associated with the light wave would be given by these, and we notice here now these E 0 and H 0 are not constants, but they depend upon x and y. So, there is some profile, so there is some electric field profile and magnetic field profile which propagates in z direction with certain propagation constant beta. So, these are the modes of the system. Okay. If instead of having n square x y, I have variation only in x direction. So, n is a function of x only, then it is a planar waveguide, and in such a case I can write down the electric and magnetic fields as E 0 of x e to the power I omega t minus gamma y minus beta z and H like this. So, here what I see that this E and H they depend only on x. So, they are the functions of x and they form the mode of the planar waveguide. Okay. And I can choose either beta here or gamma depending upon in what direction the mode is propagating. So, if I choose the direction of propagation is as z, then I can put gamma is equal to 0. Okay. Then we considered planar optical waveguide with n square of x variation and propagation in z direction. Then we had seen that we can categorize the modes of such a waveguide into two categories, two polarizations. One is TE modes, where the non-vanishing components of electric and magnetic fields are EY, HX and HZ, and these three components are related to each other by these three equations. I can have another category, that is TM mode, TM polarization, where the non-vanishing components are HY, EX and EZ, and these components are related to each other by these three equations. Okay. So, for TE modes, for example, I can form a wave equation, I can eliminate Hx and Hz and get an equation in Ey which tells me how Ey changes with x, and this is what I want to find out, okay, because I want to find out Ey of x, which is the mode, okay. So, that satisfies this equation. So, for any given n square of x, I can solve this equation, find out the values of beta and corresponding Ey. So, these are the modes. I work out first an example of planar mirror waveguide, where I have very thin layer of dielectric medium of refractive index n and width d, which is coated with metal on top and bottom. So, the refractive index profile looks like this, and when we worked out the modes of this, then the electric field associated with this is like this, and the propagation constants are like this. So, I have modes, discrete modes of such a waveguide corresponding to different values of m. So, they look like this, they look like the modes of a string, okay, modes of a stretched string. Then we consider symmetric step index planar waveguide, dielectric waveguide, where the refractive index profile is like this. So, I have a high index layer sandwiched between two lower refractive index layers, okay. The width of the high index layer is d, which extends from x is equal to 0 to x is equal to d by 2 and to minus d by 2, okay. If the direction of propagation again I consider z, then the electric and magnetic fields associated with the light would be given by this, and now my task is to find out this E0 of x and H0 of x, okay. Refractive index profile of this waveguide is given like this, where nx is equal to n1 for mod x less than d by 2, it is n2 for mod x greater than d by 2, and n1 is greater than n2. We define some kappa and gamma as kappa square is equal to k naught square n1 square minus beta square, and gamma square is equal to beta square minus k naught square n2 square. So, when I find out the guided modes of this TE modes and TM modes. So, for TE modes again I have non-vanishing components Ey, Hx and Hz, and if I solve the wave equation, the differential equation for Ey, then I find that I can further categorize these modes into symmetric and antisymmetric, because the structure is symmetric about x is equal to 0. For symmetric modes, the field profiles are given by Ey of x is equal to a cosine kappa x in the guiding film in the high index region, and it is exponentially decaying in the lower index surrounding, okay. The values of beta, they satisfy this equation. This is the transcendental equation. So, we solve this transcendental equation, get the values of beta, which are the solutions of this equation, and for those values of beta I find out Ey. So, in this way I get the complete solution, the mode field profiles as well as the propagation constants. Similarly, for antisymmetric modes, this is the field solution and this is the transcendental equation. The same thing I can do for TM modes, for which the non-vanishing components are Hy, Ex and Ez. I have symmetric modes and antisymmetric modes, and these are the transcendental equations. The only difference that you would see in between this and this is a factor of n1 square over n2 square. This comes from the boundary conditions. So, in a waveguide, a very important diagram is BV diagram, where B is the normalized propagation constant defined like this, and V is the normalized frequency defined like this, which contains all the information which you require about the waveguide and the wavelength, okay. So, I can now translate the transcendental equations corresponding to TE and TM symmetric and antisymmetric modes into these normalized parameters like this, and then I can solve these equations to generate these curves. The idea of and the advantage of generating these curves is that these curves are universal. These curves are universal. So, if I talk about TE modes, then this is the equation for symmetric and this is the equation for antisymmetric. Oh, there should not be, okay. This is the equation for TE symmetric mode and this is the equation for TE antisymmetric mode. So, let me make this correction here. TE symmetric is V square root of 1 minus B tan V square root of 1 minus B is equal to V square root of B, and TE antisymmetric is minus V square root of 1 minus B cot V square root of 1 minus B is equal to V square root of B. TM symmetric is V square root of 1 minus B tan V square root of 1 minus B is equal to N1 square over N2 square V square root of B, and TM antisymmetric is equal to minus V square root of 1 minus B cot V square root of 1 minus B is equal to N1 square over N2 square V square root of B. Okay. So, I can have the transcendental equations in normalized parameters, and by solving these equations for different values of V, I can generate VB curves. So, those VB curves would look like this is V and this is B. For guided modes, B would vary from 0 to 1. So, this would be TE0 mode, TE0, this would be TM0 mode, this would be TE1 mode, this would be TM1 mode, and so on. So, I can generate these universal curves BV diagrams, and if I now know the waveguide and the wavelength, then I can just calculate the value of V and go to these curves, find out the value of B and find out the value of propagation constants. Okay. The cutoffs of these modes are here. So, this is 0, this is pi by 2, and the cutoffs are given by cutoffs VC M for TE and TM both is equal to M pi by 2, where M is equal to 0, 1, 2 and so on. Okay. So, how the modal fields look like? So, if I take a high index contrast waveguide, I have taken high index contrast waveguide here in order to show the difference between TE and TM modes. For N1 is equal to this, N2 is equal to this, D half a micron, lambda naught 2 micrometer. So, this is how the TE0 mode would look like, and this is how the TM0 mode would look like. You can see the discontinuity in the slope at the boundaries. This is how TE1 mode would look like, this is how TM1 mode would look like. Okay. I also define penetration depth, the extent up to which the field would penetrate into N2 region. So, it is given by 1 over gamma. We have seen that these modes are nothing but the superposition of two plane waves, one going in xz plane like this and one going in xz plane like this. So, upward and downward, making angles plus minus theta from z axis. So, what we see that there is one plane wave going like this, another plane wave going like this. So, if I take the components in x direction and in z direction, then in x direction I get two counter propagating waves which give you standing wave pattern, and these modes are nothing but the standing wave patterns. So, the field stands in x direction, does not propagate in x direction, but this standing wave pattern propagates in z direction with propagation constant beta, which can be given by k naught n1 cos theta. And we had also seen that the condition for guided mode can be translated to the condition for total internal reflection. So, this is also we had seen. Then what is the power associated with the mode? To calculate the power associated with the mode, we found out the Poynting vector which gives us the intensity. And since the electric and magnetic field associated with light are fluctuating rapidly, okay, at a frequency of about 10 to the power 14 or 10 to the power 15 hertz. So, we need to take the average time average of these. So, when we do this, then we find that only z component of S, the Poynting vector, survives, and it is equal to beta over 2 omega mu naught E y square of x. This is for TE modes. Okay. So, from here I can find out the power per unit length in y direction, because y direction is infinitely extended for planar waveguide. So, the power per unit length in y direction would be given by beta over 2 omega mu naught integral minus infinity to plus infinity E y square of x dx. So, when I calculate this for symmetric planar waveguide, then for TE modes the power is given by this, and for TM modes the power would be given by this. These powers are in watts per meter. Then we had extended the analysis to asymmetric planar waveguide, where I have asymmetry here. Okay. This is the substrate, this is the cover. So, the substrate and cover refractive index are different. So, NS here is greater than NC, and what we did, we wrote down the fields in all the three regions. Okay. So, these are the fields, electric fields corresponding to modes in all the three regions, and the beta, the propagation constant, will satisfy this transcendental equation. Okay. For TM modes the fields would be given like this, and the transcendental equation becomes this. We had also defined normalized parameters for asymmetric planar waveguide. So, V is defined with respect to Ns. So, here you see Nf square minus Ns square, not with Nc, because it is Ns that will govern the guiding condition. B is also defined with respect to Ns. So, beta square over k naught square minus Ns square divided by Nf square minus Ns square. Here we have another parameter which is asymmetry parameter, which tells you how different Ns is with Nc. In normalized parameters I can have transcendental equation for TE modes and for TM modes like this. If I draw the BV curves here now, then I see that the BV curves for asymmetric waveguides, they go like this. Okay. What I notice that they do not have 0 cutoff. TE0 mode also does not have 0 cutoffs. If you look at the cutoffs, then you can see that for symmetric planar waveguide the cutoffs were m pi by 2, but now these cutoffs would be shifted by this amount, half tan inverse of square root of a, because of this asymmetry parameter. If a is equal to 0, then it becomes the symmetric planar waveguide. Okay. So, these I also notice that the cutoffs of TE and TM modes are now different. In case of symmetric planar waveguide, the cutoffs of TE and TM, both the modes were the same, m pi by 2, but now the TE and TM modes have different cutoffs. So, this is TE 0 mode, this is TM 0 mode. TE 0 mode has cutoff here, TM 0 mode has cutoff here. Now, if I have V which is somewhere here, then I will guide only TE 0 mode and TM 0 mode is cut off. So, in the range of V from which goes from half tan inverse square root A to half tan inverse NF square over NC square root of A, I have single polarization single mode waveguide, and this range is known as SPSM range. This is how the modal fields would look like. This is for TE 0 mode, this is TM 0 mode, this is TE 1, TM 1, TE 2, TM 2. We can notice that in the substrate the field extends more because index contrast with the film is less, while in the cover the field very quickly decreases, goes down to 0 because the index contrast is high. Then we worked out the modes of a step index optical fiber. So, in a step index optical fiber I have a core and cladding I have assumed to be extended to infinity. So, here I have the modes which are function of r and phi. So, this is the r solution A j l u r over A, and phi solution is cosine l phi and sin l phi. This is in the core. In the cladding the r solution is k l w r over A, and phi solution is again cosine l phi and sin l phi. Then we had defined the normalized frequency and normalized propagation constant and worked out the transcendental equations for different modes corresponding to L is equal to 0 and L greater than or equal to 1, because now I have phi directions. So, there would be discrete modes in phi direction also, so which are governed by the values of L, and the L assumes only integral values 0, 1, 2, 3. Okay. So, for those I can then find out what are the R solutions, and the modes propagation constant would then be given by these two transcendental equations. So, if I do that, so for different values of B, different values of V, I can find out the propagation constants and I can plot them. So, this is LP 01 mode, this is LP 11 mode, this is LP 21, 02, 31, 12 and so on. Okay. The cutoffs of the modes are not straightforward, they are the solutions of these equations, they are given by this, which are where J are the Bessel functions. So, by solving these, by finding out the zeros of these Bessel functions, I can find out the cutoffs. So, these are the cutoffs of various modes, first few modes. This is how the modal fields would look like. This is LP 01 mode, LP 02 mode, LP 11 mode. So, these are 3D plots, and these are the plots when you see them from the top. Okay, these are the contour intensity plots. Okay, what I see that L is equal to 0 modes are twofold degenerate, because phi solution is cosine l phi and sin l phi. So, if L is equal to 0, then there is no phi dependence, the degeneracy comes only from polarization, while L not equal to 0 modes are fourfold degenerate, twofold degeneracy comes from phi and twofold degeneracy comes from the polarization. Okay. Then we had seen the single mode fiber. In a single mode fiber we had defined three very important parameters. One is cutoff wavelength, which is given by 2 pi over 2.4048 times A square root of n1 square minus n2 square. And what is the cutoff wavelength of the fiber? It is the wavelength corresponding to the cutoff of LP 11 mode. So, if lambda is greater than lambda c, then the fiber is single moded, and if lambda is smaller than lambda c, it is multimoded. The mode propagation constants of the fiber can be fitted with an empirical relation if V lies between 1.5 and 2.5, and this empirical relation is given by this with these values of A and B. The spot size, the modal field profile of a single mode fiber, if you look back to this, it resembles a Gaussian and it can be very well fitted with Gaussian. So we can fit a Gaussian to this profile. Okay. Then we define the spot size as Gaussian spot size, where the field intensity drops down to 1 over E square of its value at the center. Okay. So W is Gaussian spot size and 2W is mode field diameter. We can also fit an empirical relationship between excuse me, W over A and V, which is given by this. So if I have a fiber, I just calculate the value of V for a given wavelength and I can get the value of W over A from this relationship. Then another important parameter for a single mode fiber is what is its band loss. So band loss is given by this. Okay. Then there are instances where we need to join two fibers together, and when we join two fibers together, then there would be losses. If two fibers are not identical, then even if there are no misalignment while joining the fibers, there would be a loss which is known as mode mismatch loss, which is purely due to different spot sizes of the modes of two fibers. If you join two identical fibers, and then there can be three kind of misalignments: transverse, angular and longitudinal, and these are the misalignment losses or splice losses due to different kind of misalignments. So this we had seen. Then in the end we had seen the waveguide dispersion. So ultimately we need to use this fiber in telecom system, and when we send pulses through this optical fiber, then dispersion happens. We had seen that in a fiber there is intermodal dispersion and material dispersion. When you use single mode fiber, then intermodal dispersion is diminished. So we get rid of intermodal dispersion, but then there is another dispersion which is waveguide dispersion, which comes out because of the dependence of mode propagation constant of fiber mode on wavelength. Okay. So the waveguide dispersion coefficient is given by this, and we can use empirical formula between B and V to calculate this factor, or we can use a more accurate empirical formula given by Marcuse for V times d2Vv over dV square. Okay. So in this way we had understood the salient features of optical fiber, how light is guided into optical fiber, what are the important parameters of a single mode fiber. Okay. So with all this background about optical fibers and the propagation characteristics of optical fiber, now we are ready to use this fiber in a system, or to use this fiber to make components and devices, which we will do in the subsequent lectures. Thank you.